All right, we're now going to look at we're going to extend what we did with the infinite charge plate. We're going to extend that to a slightly more complicated problem, and actually it's one that was on the test that you guys looked at, one of the multiple choice questions on the test. And the question we're going to try to answer is this. We're going to try to use Gauss's law to answer this question. What if I have one charge plate of plus sigma and one charge plate of minus sigma separated by some distance d? The question is, what is the electric field everywhere here? Can we use Gauss's law to solve that problem? Let's see. I want to make sure you guys got that. So sigma minus sigma separated by d. All right. So let's go ahead and choose this as our coordinate system. Let's choose a spot right in the middle. But as we'll see, it's not going to make a whole lot of difference. So what we're going to do is the exact same thing that we did before. We're going to have this. So I have some pillbox here. Let's see if I can draw that. Okay, so I've got some pillbox here. And meanwhile, I've got some pillbox here. So I've got two of these. They're identical little pillboxes. However, the charge in them is different. So what do we know here? We know here that the total E here, we know that E dot dA is equal, is equal to 2EA. We also know it's equal to Q enclosed over epsilon 0 from Gauss's law. And we know that Q enclosed is sigma A. So sigma A over epsilon 0 equals 2EA0. So what we know is that okay. That A, let's do this right. That E equals, let's see if these are equal. So it's sigma over 2 epsilon 0. All right, great. Except now we're going to take a look at this over here. Now let's do this. Let us now take a different, and we know that this is true for each of these surfaces. For one of them, when it's a plus sigma, and one of them it's minus sigma, but it's the same, everything's the same. It's just there. There's one, there's the other, right? Okay. So now what we're going to do is we're going to take these exact same things, and we're going to construct a different surface. Now the surface we're going to construct is this surface. Okay, we're going to construct this surface that's all the way out here. Okay, now the question is, what's the flux through this surface? Well, once again, these surfaces are going to give us nothing, because we know by symmetry that the E is always going to be parallel to those surfaces, and E will be perpendicular to these end surfaces, is what we know. So the only contribution we get is going to be here. So what's that contribution? That contribution is, this integral E dot dA is going to be equal to, I'll go ahead and call them E1 and E2. So I'll say we'll call this E1 over here and this E2 over here. And so what do we have? We have E1 times A plus E2 times A. That's just our integral. All that is this closed surface integral. But what's it equal to? What's the enclosed charge? Over here, I have a plus sigma A. Over here, I have a minus sigma A. So what is the total enclosed charge? Total enclosed charge, Q enclosed, is the sum of those two, and it is equal to 0. Therefore, we know that this is equal to 0. Well, that's the only way that can be equal to 0. Once again, by looking at symmetry here, the only way it can be equal to 0 is if if these E's cancel one another. So if these two terms cancel one another, we're done. Okay? So now let's go back to these integrals that we had up here before. What did we decide here? We decided that this was true. That that 2EA equals sigma A over epsilon 0. Except now we know something. Now we know that the E out here is going to make no contribution at all. The E is 0 out here. So if there's a 0 out here, then we don't have a 2EA. We're only getting a contribution from this surface right here. So we can just get rid of that. We can say EA equals sigma A over epsilon 0, or E equals sigma over epsilon 0. And we can do that exact same thing over here. It's got to be 0. So this 2EA converts to just 1EA, because this surface integral is going to be 0. The only contribution we get is that, but it still has to be equal to sigma A over epsilon 0. It still has, Gauss's law is always true. Therefore, the field inside is sigma over epsilon 0. Okay? So, we've now proven what you guys kind of worked out a little bit during the test. Okay? So, using Gauss's law, symmetry like this, we have figured out that there is no field outside these plates, and the field inside is sigma over epsilon 0. Yes, thought I misspoke there. Okay, that's that. And that's a pretty complicated problem, but we solved it with Gauss's law pretty simply.